Ryan Booz. I'm a developer advocate here with Timescale, a small but mighty team and a growing team. So as we say often, if you happen to have any interest in joining a company, really focused on trying to change the way that we use tools like Postgres and how we can bring more meaning out of data, particularly time series data, please consider giving us a look. We have, we'll put a link down below. Let me see if I have my magical captions here to do that. We might. I got an okay here. So there we go. There's our careers page. So give us a look. There's so many opportunities within this company, whether it's in engineering, whether it's in marketing, a role like DevRel. We have specific teams around Prometheus and PromScale functionality and logging, and the toolkit analytics team. Lots and lots of stuff going on. So whether you're watching this live or you watch the recording of this, consider reaching out to us. If you happen to be attending any events in the next month or two, it'd be great to see you and connect with you. Please always consider reaching out. And as always, consider joining our Slack channel if you haven't. So this is our community Slack channel down here. I can put, there you go. Look at me. I can point. Community Slack channel. There's 7,500 people, over 7,000 members in that community. And we're going to be rolling out some new tools for the community as the new year rolls around. We just want to find a way to be as helpful as possible. We're learning so much as we connect with, users of the database. And so, let us know how we're doing, what we can do better, how we can help you. It'd be exciting. So this is, I say this almost every time, right? This is going to be a, hopefully a little bit shorter stream for a couple of reasons. One, we are preparing for a lot of stuff over the next few days. Myself and David Cohn are going to be giving small presentations at Postgres Build, which actually started today. It's a virtual conference, but you can sign up and then there'll be live Q&As and some other stuff there. And then some of us will actually be attending our first live event for the first time in 2 or 3 years. PGConf New York City is happening on Thursday and Friday of this week. Again, if you're watching the stream, that may have passed. A lot of good content there. I'm sure you'll see more from that after the event ends too. And then we have some people presenting at a conference over the weekend called 𝗥𝗲𝗃. It's a Python conference, so some fun stuff there. So a lot going on. So I'm trying to make sure that all of that content is in good shape too. Let me explain what we're going to briefly try and do today. Every time, in case if you've been watching this, or if you have been watching these, sometimes these streams really end up being a working out for us of how to best articulate the feature. Certainly generates questions even as we're working. I think I ended last week by saying, here's a table, which I'll show you in a minute. And I expect that when I segment by in compression, when I group the rows by these multiple columns, I expect compression to go probably become a little bit less efficient. And it ended up being, I think in that case, slightly more efficient. I was a little bit confused by that. And then even which kind of compression Timescale is choosing. From my experience, from what I've done with users, I assumed it was one way. That's how it was explained, but never really dug super deep into a couple things. That caused me to dig deeper this week. And so this is kind of a learning process. And what it's doing for me, at least, and hopefully for you as well, is it's helping me to better understand both how a feature is being used. And honestly, each one of these weeks is helping me better articulate internally with my team and others. How do we better teach this feature? So with compression, what are the data sets that we can most effectively show and teach? There's going to be a couple things I show here today. This is honestly a little bit of a smattering because I've been trying so many different ways to demonstrate something. And I'm finding a couple things, which I'll explain in a minute, that impact how I can better show that. And so that's kind of where we're at. And the questions have been helpful. It's allowed me to go back to the engineering team and say, hey, here's a couple things, honestly, I'm not sure about. And I think we need to document better. And quite honestly, I think I need to have a better way to demonstrate some of these things. So today is really going to focus just on 2 things. I hope that means it's a shorter stream because as you've noticed, I tend to keep going. I want to find the next thing. I want to see the best way to make this happen. We're going to talk a little bit more just about the way that Timescale chooses the compression algorithm for the columns, which should be helpful for some of you, maybe to make an informed choice, or at least so you know what you can expect, right? We're then going to take, I had 2 sample tables from last week. We're going to take them, we're going to compress them and reorder them a couple different ways with and without some indexes, just to see the impact it does have. I'll be honest, I've been playing so much in the last day that I can't remember where I ended with it. So we're going to go from there. And then I just want to show you the way that one of the benefits that compression and querying data can have, particularly what we show within our benchmarking suites. When we do tests with time series benchmarking suite, TSBS, we often see, not often, we always see that in those tests, when we compress a chunk, there are certain types of queries that generally do much better. It's actually a little bit hard for me to demonstrate on a query by query basis, but I'm going to show you what happens and then briefly talk about why, when you're under load, that tends to be a better situation and you tend to get better performance. And we see this with a number of users in real life. This is not theoretical. It really does matter what kind of data you have and the kinds of queries that you're writing. So, all right, so let's get at it. Let me pull my screen up here. And yeah, I'll do this over here. So I don't know if we'll get back to this or not, but let me just quickly review this. Last week, we had, timescale compression, I think it was called, ratio and indexes. Well, we never really got much to the indexes. So I just want to briefly talk about internals, then we'll talk about indexes with you today. So other internals, we talked about this last week. And what I was not sure of, to be honest with you, is how hard coded this was. I was experiencing some different compression ratios, and I wasn't completely sure why I was experiencing some of that. So here's the example. If it's an integer, these are the kinds of encodings we attempt. All right, so we do delta delta, simple 8-bit, run length encoding, and so forth. If it's floating point, we do XOR. So if it is literally a float type, we do XOR gorilla compression. And then anything else that doesn't fall under these examples, then there's numeric. The numeric type, which we don't actually list anywhere, is actually always compressed. Currently, it's always compressed as an array type. And what that means is we just simply take all the values, chunk them up into an array of 1,000 potential things, and then we store them out to toast. And that's going to get to one of my other points here. And then we do have the data agnostic compression. So we will try things that are not number based. I hate to say numeric because there's an actual numeric column, but a number based column, integer, floating point, numeric. We have specific data type, specific algorithms for each of those types based on, what we believe and what some research has shown to be good type specific compression. Other things like text, honestly, like JSON, right? So things that are not number-like, we first will quickly attempt some data agnostic dictionary compression. So we'll basically look at the column, we'll see the, it's a little bit more complex than this, but we'll see, is it a good type for a dictionary? Are they smaller? I don't know what it's the next phase, right? Digging even deeper. But basically, is the column, the contents of this column, does it appear to be a good candidate for dictionary compression, where we say every time you have value A, replace it with 1. Every time you have value B, replace it with, now that's not a great example because you're trading 1 for 1. But this is great for naming things like cities, and you have a column that's all new textual, short textual stuff. If it gets too long, there's a length which it just doesn't help to do that, or it's too random, it doesn't really work out. Then we won't do dictionary compression, and everything else gets stored as an array type. And what that really does is take every one of those row values. We talked about how compression allows us to group up to 1,000 rows per thing, whether it's segment by or time column, however you're ordering it, and group it together. And so if it doesn't fit anything else and we can't do dictionary compression on it, Then we will basically take 1,000 items at a time in the correct ordering, and we will group them together in an array, store that array out to toast, and the compression you get from that is based on the toast compression. So in Postgres, up until I believe Postgres 13, so up to and including Postgres 13, I might be off one number on that. It might be 12. Basically, Toast had one option, which was it was called 𝗔𝗯𝗃 compression. And so Toast would be compressed with kind of a custom Postgres compression algorithm on disk, right? So the stuff as it's stored on disk is compressed. With PG14, they did add LZ4 compression as an option as well. So that's a setting you can have. And that's probably something I'll do in a future stream. We'll take a bunch of large data and just see some of the benefit back and forth of that. So that is what happens. Now, the question is, how do you know which column, which type of compression Timescale is choosing? Well, this really is it. But I'm going to show you how you can check, and you can actually see how your table is being compressed. So that's what we're going to look at from an internals perspective. So let's go do that. I will flip over to my trusty Dbeaver. So we were looking at this last week, and one of these things, ignoring all of this stuff, don't worry about all my casting. This is me playing to see what happens internally. And so one of the things that I had seen, I was playing with this. Notice I have CPU test 1, and I'm inserting the same data from the CPU table. This is a randomly generated set of data that the Timescale's benchmarking suite generates. And so, I was just saying, hey, these are, I believe they are double precision columns by default. I had switched them out to a couple different column types. And so double precision is like a float 8. And so you can have up to, I think I said last week, 15 digits of precision. And so, if there's more digits and we're doing a float, right, you're going to do gorilla XOR. And so the more digits you have to track, you will get a little bit better compression with a smaller float type than a larger float type. And so I was playing around with it. And then I was talking with someone internally, and I decided to create this table, yet another copy, and I made all of the columns numeric. And what this says, so numeric, if you give nothing, is kind of an infinitely, has infinite possibility, not really infinite, but really, really, really big. Numbers to the left and numbers to the right of the decimal. But you can also specify precision, how many total digits and how many digits can be to the right of the decimal point. And so, if you were going to always want 2 or 3 decimal points, that was good enough for you. And there's other reasons not to use, there's a lot of reasons not to use numeric. It is slower to generally process because it's not a floating point number. Computer chips generally do better with floating point numbers, and they are faster to compute because it's binary storage, whereas numeric has to be very precise. But I was just curious. And so it turns out that I was getting better compression. If I look at, and let me find that. Sorry, this is, I wasn't actually planning to come down here, but I was here. So let me just show you up here. I had created this little function, select star from compression stats, CPU, we'll do test 1. All right, so this is what we got with, it helps if you spell it right, huh? There we go. So this is what we had with CPU. This was like a copy where I was using, I believe, a float 8. So kind of there's no specified number of decimals. I wasn't truncating anything. And I got almost 70% compression. And then if I did numeric, it turns out that I got better compression, even though it's using a different compression type. Now, my point last week was this does not mean that you should go change your schemas to numeric with precision. There's always a trade-off. Internally, most people in Timescale who are Postgres experts would say, numeric has a really specific job. If you're looking for performance, you don't use numeric because the computer, Postgres, literally has to do more work to compute values because it has to take precision into account, which is slightly antithetical to what the processor does, right? If you want better compression and you really want to only truncate it to a couple of decimals, at some point, you might get better compression. You might not get the best query performance. So it really depends on what you need. And you really have to understand more of the internals of Postgres to decide, is this worth it for you or not? But that was my, I would say, my confusion last week. I was trying to understand. So I've had some communication internally about why this happened. And so here's the deal. As we said last week, so I had a float 8, which can have up to 15 decimals of precision. And then I have a numeric, which only has 2 decimals, right? So I'm storing actually, less actual a number of digits in the column itself. So what it turns out you can do, and I'm going to come down here. We have these. I'm actually going to get all of these out of the way. Just keep this separate. So we often tell you in our documentation, we rarely talk about the internal tables in Timescale. There's a couple of reasons for that. Quite honestly, we don't often want you to just go querying and certainly never modifying and just querying various things out of a lot of these tables because they are somewhat transient, right? These are Timescale's tables to maintain. We might change some of the columns, we might add, we might remove. Sometimes the meaning is specific to us. So it's not all of them are not totally tables that we would say, hey, just always work this into your process and make sure that it's happening. But there are cases. So what we would tell you to do, hey, if you want to know about your hypertables, we talk about the timescale information, right? So it doesn't have an underscore. In programming, for decades, there's kind of been this idea that the underscore is a private thing, right? Private variable. So we kind of say like the underscore timescale tables are kind of our private tables. But if you want to look at the information tables, we'll tell you lots of stuff about your hypertables. This is kind of a view, essentially, that's rolling up all of the information from these underlying tables to help you better understand. So I can see, for instance, that the CPU1 table that we're talking about, right? It's this one here. It does have compression enabled. See, so compression enabled true. It's not distributed. How many chunks does it have? How many dimensions? So dimensions is, how many columns are we distributing data by across chunks? Most of the time, on a single instance of TimescaleDB, we would say you only ever should distribute by time. You don't get much benefit by distributing by time and a space thing when it's just one server, because you're simply splitting it up over more and more chunks. But to do a query based on time, you're still going to have to go touch all of those chunks. So generally, it doesn't help in most cases. Once you get to distributed setup with multiple timescale nodes in a timescale cluster with distributed hypertables, dimensions absolutely help, and that's a good thing. So this is good information. We can also see, we can go from select star from timescale information, and we'll do chunks this time, right? And I can query these. I could say where table equals CPU. And so I do that, and we say same thing, right? So now let me just go ahead and do that, where hyper table name equals CPU. And these are all my public schema. I don't have to worry about the schema name. And so here's all the chunks. There's a number of things here, right? When does the range of the chunk begin and end? This is really beneficial when you might be looking at query plans. You want to know if it's excluding the correct partitions based on your time, things like that. And is compressed, and is it spread out across data nodes and so forth. But there's not a lot here about the actual, size, compression ratio. How is it compressed? And we get this question a lot. So the last thing that sometimes we'll tell people to do is we'll go to information, and you can see things like compression settings. Right, so now this is at high level. And again, I'll say where hyper table say name equals, and I'll say, tell you what, I'll do CPU again. So CPU, I can now see that I actually have which columns are ordered. So which ones are my segment by, right? So, and we talked about segment by last week. We'll look at that again soon. So in this case, the CPU column is segmented by the tags ID. then it's ordered by the time ID first, descending. So the most recent value is the most recent timestamp is at the beginning of my ordered array, as it were. And then it's secondarily ordered for each of those rows by, in this case, usage user, right? So usage user ordered by, ascending value. And so this will get you different results. So a lot of people ask, why would you do, so the two biggest questions we get are this: why would you order by more than, segment by more than one column? And why would you order by something other than time? And so I'm going to talk about that in just a minute. But this is where you can see that. The one thing you can't see here, however, is what is the compression algorithm that Timescale chose. So let's go look. So we have these internal tables. Like I said, the informational views are queries that we've written to bring this data into a more readable format. But if I go query these tables internally, we see a little bit more information. We actually see the ID internally of the hypertable to Timescale when we reference a hypertable in other views and other relational tables. We do things like that. But this is where you can get even more information. In case you don't know it, not something we're going to get into here, but you can, do things like, there's different states of compression. So is the chunk compressed, or is the hypertable compressed at a chunk level? If it is compressed and you've now inserted rows into it, which we now allow, that means it needs to be recompressed. We do that a little bit differently later when the query runs. How many dimensions are on the hypertable and so forth. And then when you have a hypertable, so let me find, So let me find CPU. So it's this one here. We can then see if it's compressed, where is the, what is the ID of the compressed hypertable underneath? So I talked about this last week. When you enable compression, we're going to do that on a table here in a minute. When you enable compression, we actually create a copy of the hypertable that's hidden behind the scenes. It's linked here in this table so you can find it. And it is actually a hypertable with a different schema, effectively, right? So it's no longer ints and so forth. It's effectively arrays of values, or the segment by columns are not, and they can be indexed and so forth. So this is how you can find the material, the compressed hypertable under the covers. Now you can actually find this as well. So if I look up hypertable ID 90, let's go back to this side, and I come down here, you'll see that this is the compressed side of the CPU hypertable. So anytime a chunk is compressed, it gets moved over, effectively moved over to this table. And then when you query, we transparently just go ahead and query the table as need be. You actually cannot query the results of this table on your own. You have to go through Timescale, meaning you have to go through your hypertable, which will then find the appropriate rows, decompress them, and give you back the result. So once I find the hypertable, so now let's go look at this. I'm going to go look at hypertable 90. Oh, not hypertable 90, sorry. We don't refer to the compressed hypertable by ID often in the queries I'm going to show you. We're always looking at the main hypertable, and we do the translation internally. So from the second table that we store, this is the hypertable compression. We're now saying for the CPU table, here are all of the columns. All right. What kind of compression algorithm was chosen? Now, as I showed you on the slides a minute ago and described to you, the type of the column effectively dictates the kind of compression we will use. The only difference is something that is anything other than a number-like column has the potential of being stored as a dictionary, but only after we have first examined it. If it is not dictionary compatible, or we don't believe there's going to be any benefit in that, then it'll get stored out as an array. And so this is the compression algorithm ID. This is where you can find, verify what kind of compression algorithm was used. And then over here again, you'll see the same kind of information. It's just a little, maybe not as easy to see as the view that we provide for you, right? So we can see that we are ordered by two different columns. And this view is getting pretty big, so it's hard to scroll back and forth. But the same as what we saw. So it's ordered by time, descending, then ordered by usage user, ascending. So that is where you can find the information. Then the last thing that a lot of people ask is, or that I ask is, okay, so what does that mean? What does compression algorithm ID 3 mean? Well, this is for the CPU table. Let's quickly look at the CPU table so that we can all get on the same page. I changed this table. Well, no, I didn't. I'm going to take that back. I probably did not change this one. I've redone this a few times. When you say double precision, it really is stored as a float 8 in Postgres. So these are float 8 columns. That means that when we choose compression, I should get 𝗥𝗲𝗃 compression, right? So XOR 𝗥𝗲𝗃 compression. So if we look at, type ID 3 is what was chosen here. And I look at the compression type, number 3 is 𝗥𝗲𝗃. All right, so now I can verify that that is what was chosen. There shouldn't be much, once you learn these, there's not much variation. If it's an int, you're going to get delta delta. If it's, a float, you're going to get 𝗥𝗲𝗃. If it is numeric, you're going to get an array. If it is something else, that might be where it's valuable to look. Were you able to get dictionary compression, or did we just, again, put it back out as an array? So that's what this does. If I look at a couple other columns, you'll see, for instance, that I segmented by tags ID. Therefore, there's no compression. And we saw this last week. If I now go look, let me actually go find that for you. I said I would do this. So let me go find that table again. So you can query this table. It doesn't mean that it's, why am I doing that? You can query it. You're just not going to get as useful information as you would hope, right? So if I say select star from Timescale DB internal, and we'll do compressed, oops, what I meant, compressed, and this just hasn't updated. 𝗔𝗵𝗽, I haven't refreshed. That's why it doesn't show hypertable 90. So I'm just going to select that and then change this to 90. And I'll limit this to 10. Oh, from, that was easy. Oh. Type coding is fun, isn't it? Start from, oh, well, there we go. It came back. So you'll see that I don't get what I expect, but I can actually start to look and work with this table, which a lot of people don't recognize. And there's one specific reason why you really care. We can see, though, because we segmented, here's my tags ID. So every one of these rows represent tags ID number 1. If I keep scrolling over, these are all the data columns. There's 10 columns in here. Over on the side, we get some good stuff. So number 1, how many rows did we fit in each segment? In this case, for these number of rows, we're getting 1,000 hypertable rows per 1 row of compressed hypertables. That's cool. And then it turns out that the sequence number is what we often use elsewhere. All of these TS columns, _TS columns, these are meta columns that we can add onto the table, onto the row, which the query planner, if in Timescale, we can actually examine these values as we go. And so we add them as meta information. And so the sequence number is what helps us find rows in order. So once we identify where rows start based on your a range for your order by, in this case, it's ordering by time and then the max user, usage user, we can identify where those things lie, and it's actually faster to scan then by the sequence number once we know where to go. And then you'll see for every ordered by column, you'll see the min and max range within that group. So it helps us identify your query looked for A, B, and C. You ordered by those columns. So first we go to tag ID 1. You're looking for a specific range of time. Does this row, which represents 1,000 individual rows, do any of those 1,000 fall within this time period? Oh, they do. Okay. So now, do any of the values fall within the min and max? And if it doesn't, we can filter those rows very quickly without having to worry about decompressing and scanning every single row. That's how we use these things. It can be really beneficial. So those are the tables that you can go look for some of this information. So now let's go talk about how that actually impacts some of the compression stuff that we're doing. So let me find the queries I've been playing with. All right, so first we're going to look at, again, I showed you this. I think this is one I was just looking at. Yeah, CPU table. We're ordering by time and usage user. So one of the things that you can start to think about here, so these first couple queries, this is where it's hard for me to show you without doing a larger demonstration, which I'm trying best to figure out how to do for a future stream. One of the things that you'll see is I'm querying in this case. This is approximately, I'm looking at one tag, and in Timescale benchmark and time series benchmarking suite, a tag is like a computer. So we actually refer to them further down as hosts. All right, so here we're saying host something or other. So these are values based on a host. So I'm looking at a specific host, and this is maybe 3 days of data. We'll say roughly 3 days. When I analyze this, the number one, it happened very quickly. We're getting, oops, that's not what I meant. Let me run that again. Somehow I lost that. There we go. We're getting a total of 17,000 rows back. All right. And it took us about 7 milliseconds. One of the interesting things here is how much data we had to go fetch. So I'm using analyze and buffers. Buffers will show you how many disk pages, whether it's actually on disk or in memory, how many 8K pages we had to go examine to get this information. Now, because the compressed table is smaller, there's many fewer rows, up to 1,000 fewer rows, 1,000x fewer rows. Because there's so many fewer rows, we don't have to go examine as many pages to figure out where to go find the data, generally. This doesn't always work out, and this data set is actually a little bit tough to demonstrate that sometimes. In this case, I did not quite the same amount of data. So let me do 31.2. Let me do, all right. So if I do another 3 days of data here, you'll see that I end up with, not quite twice as many pages. And that's simply because these are very small pages. These are all integer values. So this is one of those areas where you might not see as much. You'll see speed up. You'll definitely see a space savings, right? Numeric delta values can save 95, 96% of your storage space because it's so efficient to compress them. Querying wise, however, it still is just integers. So the rows themselves are not very wide. In this case, they're not really big values. They're just, smaller integer values. And so we are querying more pages from disk, but not that much more. In this case, I actually went back and it looks like I hit a compressed hyper table. I didn't expect that. So let me quickly see. So here's what we're going to do. We're going to select start from TimescaleDB information, where hypertable name equals CPU. All right, so I have these 5, and let me see where the range end is. So it looks like this chunk has gotten compressed. So normally, I didn't think that would happen. I must have run a compression of some sort. So here's what we're going to do. We're going to uncompress that chunk. And here's the deal. Decompress chunk. And then we say this. All right, let me uncompress that. Now, why am I doing this? Now, this is the most recent chunk, and our actual guidance is that the most recent chunk, at least, should stay uncompressed. Sometimes maybe it's the most recent 2 or 3 chunks, whatever your specific query pattern might be. So if you're always modifying data for, let's just say It's an IoT application. You get lots of data every day, but you only modify the most recent day of data. Maybe your chunk size is a day, your chunk time interval is 1 day, and you keep the most recent day then, or the most recent 2 days uncompressed, because it's much more effective to insert and update data because number one, you can update, you can delete from a regular hypertable, but if the chunk has been compressed, you can only insert. You can't update or delete currently. And the other value there is, particularly in things like IoT, we're often looking for the most recent values. And it turns out that indexes with regular row data is really, really efficient at finding the most recent value for a particular ID of some sort if it's indexed correctly. With compressed data, even if the data is ordered, we still have to decompress the row. And so it actually ends up, in many cases, being a little bit slower to find the most recent value in compressed data. Now, if you're trying to do an average over all of that data, it's probably going to be faster with compressed data. So we normally expect this. And so now I think you'll see that we do a lot more reads. So now we hit 400 and some pages. If I run this again, it's now going to be cached. So we hit 500 pages of data from the most recent for 3 days worth of values of all of this information. It still ended up being, let's see, this is 25,000 rows. And from here, we ended up hitting a lot less data, about 4 times less. And it was, in this case, maybe twice as fast, something like that. And so you can get data out when you're looking for very specific things, specific columns. We can get the data out really quickly by compressing it. Now, again, this is a pretty small sample size. This is a total of like 100 million rows. I'm querying a couple days worth for a specific host. And so it's hard to demonstrate really large values. Where this matters, and I'm actually going to go over here. I didn't plan this, but I'm going to head over here, and then we're going to talk about indexes. So here is, let me go ahead and grab this. Oh, let me show you that. This is actually from source. I got talking with one of our developers. This is how we determine which column or which compression algorithm to use. So there you go. It's in code. You can go see it. It's an open source project. Let me go to the blog and let me just show you this. So I refer to this again, not because I'm trying to specifically talk about, in this case, ClickHouse. We have a number of these benchmarking. That's not my point. I literally don't care about that at the moment. What I want to show you is why, we were very transparent in this example, actually, when it came to querying. And it turns out the query latency in a lot of cases improved, right? So in all of these yellow cases, Timescale was faster. And there's a reason why this worked. We compressed, just like I showed you, all of the data except the most recent chunk. So the last point query, if data is pretty regular and your last chunk is big enough that it's getting recent data from all of your devices or what have you, an index on the last value is a really, really fast query. Whereas other kinds of databases that do, in this case, a merge tree kind of setup, it's just not as efficient. It has to query a lot more data to get that. But one of the things we saw, and we actually talked about it down here, and I'd have to go find it. This was a long blog post, huh? One of the things that we saw was that, I forgot how long this was, so my apologies. Wow, there we go. When you see some of these numbers, you see values like 2.8 milliseconds, right? So 2.48 milliseconds for this group by. This was running 1,000 queries at once across 16 threads, right? So it's as if 16 things are asking for a random chunk of time as fast as possible. This is where you see more of the speed up. It's pretty hard to demonstrate here, right? I'm querying this. I'm getting this back in 7 milliseconds. I'm querying the uncompressed data. It's taking 13 milliseconds, but that's a 2x, difference. It's not that big. What it turns out, however, is running these queries, a bunch of queries at once against compressed data, when it's this kind of information, actually performs better over that long haul. And so now, if I ran these queries, when I ran these queries for this benchmark on uncompressed data, the numbers were maybe, in this case, I actually don't remember. It would take me a little bit of time to go find. But instead of 2.48 seconds, it was maybe 15 milliseconds. These are milliseconds, my apologies. And the reason it was maybe 15 milliseconds is because it was having to shuffle a lot of more data off of disk the further back in time it went. And so when you turn on compression, all of those queries end up being more efficient. And now you can service a lot more queries. And that's one of the values and the beauty of compression within TimescaleDB. It doesn't work perfectly for everything. There are some queries that we're recognizing, hey, we can do better on how we aggregate and group some of this data. And one of the ways we can do that is through some vector operations. And it's something we're talking about. I'd love to understand that more, how we might be able to better do that. So this is one of the ways that can happen. And the reason the last point is so much more effective across 10,000. So this query asked for the most recent value for 10,000 items, and it happened on average in 103 milliseconds. And the reason it was able to do that is because of an index. They're all in the most recent chunk. It's not compressed. You can very quickly look at the exact index for that column and that timestamp and get you the value back. If it couldn't find all of them, then it would have to scan back into compressed hypertables, and it would take a little bit longer. All right, so that's what's happening there. So let's go back to 𝗔𝗵𝗽. And so in general, that's one of the reasons we say, in this case, I'm ordering by usage user, descending. So I'm getting all the values out. You'll see that does have a sort. In this case, it may or may not have a sort. Yeah, it still has a sort there because I'm getting more than the one column out. So it has to make sure that the IO weights is in the same order and so forth. But you can actually get just as much value. You can get a little bit more effective value out. If I take a query like this, it might be even faster. I can't say this for sure, so I apologize. This doesn't work ahead of time. I have an example query, but for some reason my brain is not. Oh, let me do this. See if that gets rid of the sort. It does. So notice that now it's even faster. Right now we're down to 3 milliseconds. And the reason is because I asked it to order by the way that the value is already sorted in the compressed chunk. So now it knows as soon as it finds a value, a row that corresponds to this, it can decompress it and it can just start streaming it out. It doesn't even have to use any kind of sorting memory to do this. That's the other way that you can get a lot of speed and benefit out of compressed hypertables and chunks that you can't get here. So even if I say order by time descending and usage user, oops, that down here, forget this. So this is the uncompressed portion. Let me do time descending. We still end up with, now we're like 12, we're technically thousands, hundreds of times faster here, right? We went from, I guess, four or five times faster. We went from 3 milliseconds to 12. Had to get more pages, and it still had to do some sorting in memory, right? So that's some of the benefit that can happen by doing ordering, thinking this through. If you're often going to order by a value, and this is what's happened for some users, it's really helpful to think through how your data is going to be ordered. And now you know where to go find that information, both in the informational views and a little bit deeper, if you want to, into the catalog views to see the hypertable compression. That catalog view will show you all the details, column by column, how it's being compressed, which ones are set for sorting, and so forth. All right, so you can go find that information. And just to show you, I'm not going to take the time. It'd take me a little bit too long at this point to decompress this. There's some other things in here, right? So we have, this was our group by. You'll see that when I do compressed data for so I'm decompressing chunk by, these are two chunks I'm decompressing. There's two decompressed chunk nodes. right? We find it based on the index of the tag, and then we're filtering based on a timestamp and based on, no, just a timestamp, my apologies, because the index is for the tag. And so we do filter out some rows as it's being decompressed. Still pretty fast, 20 milliseconds. If I take that same one, and I'm going to just up this to, so I'm sure I'm in a compressed chunk, and that was for 5 days. So let me just make sure I'm in chunks. And this is about the same speed. And so this became a little bit harder for me. Some of this is because it's in memory, most of it's in shared memory, shared buffers. We're still getting the same amount of rows out. We do have to take the time to decompress. Where you see the benefit here, again, is when you're doing lots of queries. Because we're actually doing less reading from disk to get that information out, and array decompression is really efficient for us. When you have lots of activity, although these queries as one at a time are almost exactly the same speed, right? I'm decompressing 21 milliseconds. I'm not decompressing, and it's 18. So maybe slightly slower even for compressed. If you do a lot of queries against this, you actually usually end up with better performance overall. And if you order this appropriately, you'll see that you get, so this is max usage user. I don't know this is going to make any difference, but let me go ahead and try. Order by usage. Oh, it's not going to work. Probably isn't going to work. And we'll do that. Yeah, it's not going to work because it's not what I had accrued by. It's not how I had it ordered on disk. So that's one of the benefits. You'll get compression will just help you with a lot of queries at once. And when you have particular ordering, so when you're not doing aggregates, you can get really fast values out of the database. So number one, it's going to win because a lot of connections, compressed data, more overall throughput. In most cases, I don't want to give a blanket statement there, but in most cases, that is the case. And then with aggregates, usually the more connections you have, the more queries you have going. Because we're getting 1 or 2 rows at a time that represent thousands of rows, you can do more throughput over time and you get more value. And then when you just need to get those values out, if it's ordered by the order by column, it can just start scanning all the way out. And the reason you can't do that with a regular table is, remember, it's everything's on a heap. And so even though the values may be sequential, if you've updated anything, if you've deleted data, your values that are sequential by time might end up on different pages on disk. And then you don't have, you still have to read, you actually have to read more pages to get that information and sort them and so forth. So unless everything's available in an index, and an index that's well maintained, you will just get more throughput actually streaming values out from a compressed hypertable. That's a lot of info. There's a lot there. So many more examples that we need to get better at having. But just we're digging deeper every time we go. That's some of the value you can get through. I think the other thing to show here is, I'll just do this last one and then we'll talk about indexes. This is, again, pulling from a compressed hypertable. It takes 2 milliseconds to get the max of all of these values, right? For a very small time range. This is a few hours of time. So it didn't have to get many rows. And because I'm looking for the max of each value, it really fast to go each of those columns. Now, doing it from an uncompressed hypertable is actually a little bit faster as well. But I think, as we've shown with each time, the values are really close, 1.9 milliseconds, 2.7 milliseconds. You'll eventually see the throughput is increased if you're doing lots of queries. It's just hard for me to demonstrate that here without doing something like TSBS. So maybe we'll do that in another episode at some point. All right. So hopefully that just helps think through all the possibilities. Okay, now I have a compressed hypertable. I see what segment by does. It's helping me group up to 1,000 rows of data per row of compressed hypertable. I now know where to go find the compressed hypertable. I can now see how things are compressed. All of that's happening. What about the index portion? So this is the question we get often. So I just want to show you this today so that you can get an idea of how this might be impacting your queries. There is one thing we do currently which I am now giving this recommendation to most people who show up at Slack asking about compressed hypertable queries. So you do have to think about what you want to segment by. So I gave an example table with sensor data. There's somewhere around 70 million rows in here for the last month. I don't remember. We could go find it in just a second. A lot of people have something like this. I have a sensor. I show this often. This is from a previous company. I have a sensor, and internally it measures multiple things. And so I store that in my hypertable. This sensor reported at 1 in the afternoon. It gave me 5 measurements. It reported at 1:01 in the afternoon. It gave me 5 measurements. These are the measurement types. And so I see this schema pattern a lot. And so then what happens is, in your case, in most cases, you would then create at least an index on those 2 things, because you're often writing queries like, so I created this hypertable, made it 7-day chunks. I made sure it had indexes that I would expect to find, and then I inserted data. All right, like I said, about 1,000, a million, 100 million rows, something close to that. So let's see how much is in here. So we have 96 million rows in here. All right, minimax, oops, not sensors, sensors narrow. And so it's from the beginning of the month until today. And then I wrote a couple queries down here. So here's from sensor narrow. So we have one bucket. I'm ordering by, I'm asking for sensor ID 5, measurement A. And I'm going to do it based on, I'll say, last week, less than or equal, I'll just say now. And I'll say 1 week. So this should generally be uncompressed. What do I do now? And interesting. See what I did here. Let's look at our data. It's the fun part of live stream. And, not limit 10. Let's do limit 100. And I have an ID 5. I'm sure this is really, let me just do that. Okay, so that makes sense. This is fun. Greater than now. Oh, greater than, isn't that funny? Isn't that funny? Of course it can't be greater than now. All right, let's do that. That's so much better. All right, this is running for a week of data for this sensor and this measurement type. Now I would expect that it's going to use, this is fun. There's a lot of data here, so that was my bad. Wow, this is when I need to have jokes. And I'm actually surprised that it's taking this long. It could be because, actually don't know why. So here's what we're going to do. We're going to explain this and see what it thinks it's doing. We're not going to analyze though, because that would actually run the query. So it thinks there's, my guess is index condition. So it does have that. So it's using the index that I would expect. It's doing a recheck on it. My guess is that maybe the row estimates are off. So this is fun. Oh, 1 day, that could be the other part. That's a lot of data. So let's do 1 hour. And just for the sake of this, we're going to do 1 day, just to make this a little bit more quick. Okay. It's out. Yeah, I actually haven't analyzed these tables since I've been playing around. So that really could be part of it. My row estimates could be pretty far off. So this was for, oh my goodness. I got this totally backwards. That's why we were doing way too much data. Okay, that's much better. So we got 24 rows or so. Wow, how about that for live coding? And so if we explain, analyze that, and I always like to do buffers, see that we're reading 5,000 pages to get this information, and it did use the index condition right away. That's great. Everyone's happy. So now we're going to go ahead and compress. We're going to do, I have it up here. So we're going to compress this. And I'm going to segment it by sensor ID and measurement, because I know that in my case, I'm always going to query by sensor ID, and I'm going to query by the measurement type. I graph each kind of measurement. I'm using working with a user right now who's doing this with some really interesting, seismic data. Yeah, I don't know. I think I'm saying that right, for like vibration on the earth for earthquakes and so forth. It's very similar. So they have a bunch of stations and lots of different kind of measurements every time they get a value in. So they query by each one of those. So it would make sense that you would want to try and get the fewest rows possible. So we're going to go ahead and set this up. Then I'm going to show the chunks. You know what? And we're going to let me see. We're going to order by I offset 1. Let me see if that works out. Oh, that's not what I meant. Order by I descending. There we go. So we're going to go ahead and compress everything but the most recent chunk. This shouldn't take too terribly long. And now, I would say that it's fun when I get it wrong. So basically, I'm showing all the chunks, ordering by the name, descending. So the most recent chunk will be at the top. I'm going to skip that chunk and do all of the others into compressed chunks. So this is doing 4 chunks of compression. Should be done soon. And with this, it was 2 ints, 2 floats, and then these 2 ID columns and a time column. And I meant to say, in case you didn't notice that, I said something wrong earlier. We show this in our documentation, however. Timestamps are delta encoded as well. We translate them into values that we can do delta encoding on, which is fun, right? So it's, this is your timestamp. The next timestamp is an offset of however many, microseconds or milliseconds and so forth. And that's a delta encoding, change row by row. I didn't think it would take this long, so I'm going to keep talking about what we're going to do. We'll look at the compression. We'll go find which hypertable it is, and then we're going to look at the indexes on that compressed hypertable. Remember, I have an index on the regular hypertable by sensor ID and measurement type. Everybody I know expects that index to carry through, because we don't compress the segment by columns. We leave them as columns that we can index. It turns out that's not what happens. It's something we're talking about internally. We create a separate index for each column, which means that your queries then are actually a little bit less efficient. The way that Postgres works, we'll look at the most primary index, the one that has the densest. Words are escaping me at the moment. The densest amount of data, so we can kind of prune rows as quickly as possible, but then we filter based on the other one. Okay, I really didn't expect this to take this long. I may have put a lot more data in here than I did previously. I forget how much I ended up doing yesterday when I was preparing this. So that could be part of it. These chunks might be fairly big. So I wish I could tell you how long it's going to take. And then I want to show you these last 2 things will be done for the stream. I assume it will happen here soon. Could be a bad assumption. And if there's any questions, that would be great. Otherwise, I really do want to end the stream here in a minute. It's where I need like the music in the background, or it'd be nice to have someone else on the stream with me. We've just been, like I said, it's a busy week. Schedules trying to get someone else to banter with a little bit. What I hope didn't happen is sometimes I actually lose a connection behind the scenes, and that's the one area where Developer is not the best at showing that. And so it looks like it's working, but it turns out it's not working. So I feel a little bit like I'm not sure what I should do here. There we go. Hey, it worked finally. Whoo, my apologies. This is not a big machine. This is actually a pretty small VM. So here's the compression stats. We got 94% compression. Huge. Oh, there's 18 gigs of data. Okay, there's a lot of data in there. All right. So let's at least give it that. There's a lot of data in there. And now that same query, right? So if we do a day, we're gonna read that same amount of data, right? So we got, so now we're doing compressed chunks. Look how much less data it had to read. I'm striking out here. It is, yeah, so it's less than now and greater than 1 day. So I did not expect this to be compressed data. I must have had that wrong. So let's do this. Let's at least go show you this. Here's the hypertables. So we find sensors narrow. So it is hypertable 88. I'm going to go way over here and see that the compressed hypertable is 91. So I'm going to look up the indexes that are stored in Postgres for a compressed hypertable 91. And you'll see that we ended up with 2. And instead of the combined index, it's called a composite index. It has sensor ID and measurement type. I get 1 for each. All right. And I keep going over. You'll see that it is just individual. And so what happens then is if I look at this explain analyze, we actually lose out a little bit, because what happens is first we do an index scan based on the sensor ID. Then we have to filter out rows as they're decompressed, or filter out rows based on the second index, instead of just finding the however many rows that ended up producing. That ended up producing a total of 33 rows. So we threw out, in this case, 66 of them, right? There were 99 rows for this time period for this sensor, and we threw out a third of them because I had 3 measurements, A, B, and C. How could we make that more efficient, particularly when you have more things? So this is what a lot of people are not fully aware of. And so we're going to take that, we're going to find that hypertable, right? So we know it's 91, and we can say create index. I'll just say IDX compressed segment by measurement on TimescaleDB internal dot compressed hypertable. In this case, it's 91. And we say columns sensor. And then we want to make sure we do the TS sequence. And I'm going to forget this at the moment, so my apologies. Man, I can't believe I'm forgetting that at the moment. So here's what we're going to do. We're going to do, this is one area that we need to improve documentation. We know that. So we're just going to do from, what did I just do there? Internal dot. All right. So all the way over here, we have the TS meta sequence number. So that is beneficial to the decompressed node. So I'll bring this down here so you can see it. So that is beneficial to the decompressed node that we provide. That's the operator that works on your data. Measurement. Oh, type. My bad. Measurement type. I create that index. And now we should see that it uses that index, and it does. So I'm no filtering. I'm only getting the 33 rows out, right? I'm just getting the 33 rows. So it's actually a more efficient query than it was before without this index. Now this is smaller. These chunks aren't terribly big. There's not lots and lots of rows. This definitely has an impact the wider you go. All right. So the more sensor IDs, the more measurement types that you pack into a compressed chunk, can really this can really benefit that. And something that we're talking about, do we just do this by default? I wasn't around for the original design. I can't tell you exactly why we chose to not create the composite index. Might matter, obviously it matters which order. So I could get rid of the other two indexes, which actually make this smaller, if I'm always going to query by sensor ID first. If I'm going to query by measurement ID, then I need an index on that as well, or you get worse performance. All right. So that's, there's a lot there. Yeah, foo, right? I know. The reason I think it's not a big machine, and the reason I think it took a long time, I have no idea what else is going on in this. I have so many tabs open. That's part of it. But 18 gigs, hey, 18 gigs down to a little bit more than 1 gig. That's a pretty good compression ratio. I'm happy with that. And the speed of the queries is still, really efficient. So I guess that's what the last thing I was going to show. If I decompress, as always happened, I'm now just over an hour. There's so much to talk about here. This is decompressed chunk, 8 milliseconds to do this average of values. So we're doing the average of 5,000 values effectively, right? So that's pretty quick, pretty efficient. I basically had to query just a couple rows of a compressed hyper table. That's really awesome. If I were to find an uncompressed chunk, let me do that. My apologies. Select star from TimescaleDB information.chunks where is compressed equals false and hypertable name equals what did I call this one? Sensors narrow. Well, what do you know? None of them are uncompressed. So let's do this. All right, so let's pick the most recent one. I obviously did something wrong. It's this one right here based on range end. So we're going to decompress this chunk just so I can show you this. And the range ends starts on the 24th. So select decompress chunk TimescaleDB internal. All right, let's decompress that. And I'll just run this query so we can see what it does. And this then has that index on sensor ID measurement. So it should function very, very similarly to the compressed chunk. There should not be a filter necessary based on the timestamps and the sensor measurement. Hopefully this doesn't take nearly as long. I'm guessing this is going to take about 35, 40 seconds based on how long the other one took to decompress one chunk. And then we'll see what the difference is. So hopefully it's helpful. We could banter about this kind of stuff all day long. I will say that every step of this for me is helping better inform. In fact, one of the things we're going to talk about as a team this week when we're on site for the first time in many, many months at PGConf is for some of these features like compression, how do we best work with and walk someone through a feature like this so that we can identify your kind of data works most effectively when you do this. So that's the opportunity or the hope. All right. I was wrong. Not 40 seconds. Can't take too much longer because it's one chunk. And decompression is actually a little bit slower because we have to create the space first so that it's ready to insert with the decompression. So it is a little bit slower going the other way. All right, I'm ready though. Before this was a few milliseconds. Now, let's see, this is not, so this is not in, here's why it's a little bit faster. And I'm only doing, so 1 day's worth of data. The other one might not have had a full day. Right, we have an index on time as well. And so we can really specifically go right to those rows. It still is pulling out 5,000 rows, I think what you'll see is if I were to start querying more and more data, so if I go back maybe 5 days, we have to sort some stuff, we're querying things. There's no decompressed chunks here. We're up to 15. However, if I go back, I don't know, say interval, we'll go back 10 days and 15 days. Oops, I did. So there's some decompressed chunks. We got a lot more rows, I think, in total, 12,000 rows. So we're getting a lot more data out. Look at that. We got a total of, so my estimates are pretty far off. I probably need to analyze this once it's been compressed. Still 30,000 rows, a lot of stuff pulling out as we do averages and so forth. And again, if I were to be hitting this over and over and over again, I'm getting the best I can, and long term, I would actually be pulling out less data. And so that's pretty cool. All right, I'm done. I've rambled on for way too long, and not because I like rambling. I just like trying to figure all this stuff out. I am doing less actual page work. This is uncompressed. So 300 and some pages to get that information. I'll go back 20 days. This is on compressed chunks. Well, now it's in. Whoops, I must not have hit something compressed. This is hard. Oh, I'm doing multiple chunks now, so I span chunks. Sorry, it's hard to always show you everything, right? Anyway, hopefully a couple of these things are helpful, particularly the indexes, knowing that you can go add your own index to get back to that composite column if you have it. Ordering data can make pulling it out much more efficient because you don't have to go get multiple pages. We can just get an array, stream it, get an array, stream it. That's where compression can really have a lot of value as well. Thanks so much. Appreciate a couple of you that stuck around, and hopefully this is just going to be beneficial to watch later and helping me learn this every day as well. Thanks so much, folks. Have a great one. Take care.